The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Settle down. I want to draw your attention to the fact that the final exam schedule is out. It's been out for about a week, and 3091 final will be on Wednesday of finals week, which puts it on the morning of the 15th of December. Well, that'll be a 3-hour extravaganza, celebration of learning, where you all come to show me what you've mastered, and it's going to be just a grand time. And it'll be over in the Johnson Athletic Center. So I urge you to take a look at the final exam schedule and make your travel plans as soon as you know what your last obligation is, because things are going to get booked, and it's going to be harder and harder to get out of here, and certainly to get out at a decent price. Last day we looked at electron domain theory, which allowed us to predict the shapes of molecules. And this is taken from the book. This is table 4.3, and I've highlighted in orange. We worked through some of these molecules last day, the SF6, BRF5, ICL4-, and then we looked at the series CH4, SF4, ICL4-, and we saw how by counting the number of electron domains and then partitioning them into bonding versus non-bonding domains, we could proceed in a systematic manner towards the deduction of what the molecular shape should be. So that was a productive day, and I urge you to understand what's going on in table 4.3. You can expect that you'll be tested on that at the end of October. You'll have an aid sheet, so you probably want to know how to work through this this document here. So today I wanted to continue this treatment of covalent compounds, and specifically I wanted to talk broadly about how we determine state of aggregation. In other words, how do we determine whether something is going to be a solid or a liquid or a gas? We've already seen that ionic compounds, by their nature, because they have unsaturated bonds and they continue to allow more ions to glom onto the initial starting point, results in a large aggregate. Large aggregate, tightly bound, leads to crystal formation. The crystal is the regularity, but definitely solid formation. And when you're trying to answer the question, is something a solid or a liquid or a gas under certain conditions, this is the subliminal message. You have to compare the cohesive forces versus the disruptive forces. So the cohesive forces are the binding forces, and the disruptive forces typically are thermal in origin. So we have to compare the binding energy of the substance to the general thermal energy. All right? And that's shown here. So binding energy, then that gets back to the nature. So if it's an ionic compound, this binding energy is that Madelung-bearing crystal lattice energy, and it's very negative. For sodium chloride, it's about 787 kilojoules per mole, whereas the thermal energy in this room is about a 40th of an electron volt, so that's small. Sodium chloride is a crystal at room temperature. So now I want to turn to covalent compounds and ask the same question. What's the state of aggregation? But there's a fork in the road here. There's two types of covalent compounds. We saw, as is shown up here on the slide, the results when we have just the single molecules. But we also saw at the end of last lecture, it's also possible to talk about covalent networks. We looked at diamond and we looked at graphite. Now in the case of diamond and graphite, we're in a situation that's similar to ionic solids. In other words, we have large aggregates because the sp3 hybridization allows for carbon to bond to carbon to bond to carbon to bond to carbon, and so you end up with a large aggregate. In fact, it's an ordered aggregate. It's a crystal. Diamond is a crystal just as sodium chloride is a crystal, but both of them are large aggregates. And we saw also that the binding energy in diamond is very, very strong, very strongly negative, and so therefore it trumps the thermal energy of the system. So these are solids at room temperature. How about molecules? That's what I want to focus on today. What is the nature of binding in molecular systems? And specifically, let's just take one of the molecules we looked at last day. We looked at sulfur hexafluoride, and I told you sulfur hexafluoride is a gas at room temperature, even though this thing has a very, very high molecular weight. So the question we're really asking is, what are the forces that would cause sulfur hexafluoride to bind to itself? And so far what we've been looking at, electron domain theory, doesn't answer this question at all. Electron domain theory treats what's going on inside the molecule. Okay? It treats intramolecular bonds, intramolecular bonding. Okay? This is between sulfur and fluorine. Sulfur and fluorine. Okay? And this is a very strong reaction, and it's referred to as a primary bond because it's the first bond that forms. If I look at the world from the vantage point of sulfur, the first bond sulfur encounters is this primary bond to its neighboring fluorines. But now I want to ask, how does this molecule, which we know is net neutral, how does it bond to another one like it? So that now means we have to shift. So state of aggregation is not determined by this at all. State of aggregation is determined by intermolecular forces. Intermolecular forces. And they're different. They're different. So what we want to do is look at the intermolecular forces. And for that, we're going to go through this catalog. Now, that's last day. This is what we're going to do. We're going to go through this catalog. So I'm going to show you 4 different types of intermolecular forces. We're going to go about them systematically. The first one is dipole-dipole interactions. Dipole-dipole interactions. And clearly, this interaction occurs only between polar molecules, involves polar molecules. So these molecules have a net dipole moment. We could model them as dipoles. And so if this is, for example, an isolated molecule of hydrogen chloride, we know we've got a strong covalent bond within the molecule. And we know the shape of the molecule. It's linear. But how does this hydrogen chloride bond to another hydrogen chloride? Well, we can see that this is delta minus, this is delta plus, and so this delta minus end is attracted to the delta plus end of an adjacent molecule, and so on and so on. So this is a dipole-dipole interaction that, when the temperature is low enough, the thermal energy will not disrupt the bonds that are forming by this dipole-dipole interaction. So it's operative at low temperature. Operative at low temperature. And these are all weak interactions. Everything I'm going to talk about today is weak by an order of magnitude in comparison to the primary reactions. So if we compare ionic bonding and covalent bonding, primary covalent bonding with this sort of thing, this is down at around some, on the order of about 10 kilojoules per mole. Whereas up here we're talking about hundreds of kilojoules per mole. So these are very weak, which means that at room temperature, HCl is a gas, sodium chloride and diamond are solids. And there's the energy in a dipole-dipole interaction. I'm not going to give you the full formula, but I'll just give you what it's proportional to. Clearly, it's going to be proportional to the strength of the dipole. Stronger dipoles will bond more tightly than weaker dipoles. And in fact, it goes as the 4th power of the dipole moment. If mu is the dipole moment, stronger dipole moments give much, much stronger interactions than weaker dipole moments. And the dipole moment is proportional to what? It's proportional to the charge and the separation. The charge and the separation. So if I've got more charge separated by a greater distance, I construct a greater dipole, a dipole of greater strength. And in the denominator, we have the cube root of the interdipole separation. So really what we want is very strong dipoles spaced closely together to give us the strongest reaction. Okay. And here, example HCl, I've used this in some of my own research, and this thing has a melting point. HCl has a melting point is minus 115 degrees C, and the boiling point at atmospheric pressure is minus 85 degrees C. So if we go down below minus 115 degrees C, the thermal energy is low enough that at that and below temperatures below this value, this weak interaction dominates, and we have solid HCl. Second form of interaction, and these are all cataloged in Chapter 8 of your book. This one here is a little bit premature, but all the books do it, so I'll just, for completeness, I'll go through it. It's really involving solutions. See, this one was HCl to HCl. It's answering the question, under what circumstances is HCl solid, liquid, or gas? This one here, this is called dipole-induced dipole. So this is really two different species. And you can see in the cartoon, the left has HCl, hydrogen chloride, and the right has argon. So this is bonding between two different types of species. So for example, if I were to mix HCl, it's a gas at room temperature, argon is a gas at room temperature, I mix two gases at room temperature, I have a gas. But at low enough temperatures, I will get a liquid, and at low enough temperatures yet, I will get a solid. It'll be essentially a solid alloy of HCl molecules and argon atoms. So what holds that together? Whenever you see a solid, you must conclude that there are forces that bind the species together. Things don't just sit there because they're lazy. They're bound. So what are the forces that could bind a condensed form of argon and HCl together? And the answer is dipole-induced dipole interactions. Dipole-induced dipole interactions. So this is a bit of a departure, but it'll come in handy in a little bit. And this is present in solutions. Present in solutions of what? You need one polar of a polar and nonpolar species. Polar and nonpolar species. They could be atoms or they could be molecules. It doesn't matter. So how does this work? Well, here's the nonpolar molecule. This is argon or helium or one such methane. Nonpolar. So it has uniform distribution by definition. If it's nonpolar, there's no net dipole. So here's the nonpolar entity, nonpolar species. If I bring up a dipole in close proximity, what can happen is the following. This negative end of the dipole interacts with the electron cloud in the nonpolar species so as to cause repulsion. So this cloud, it's in motion. The electrons are not potted. And so the presence of this negative end of the dipole actually causes the electrons to flee. And so we get a maldistribution in the electrons. And in fact, this end becomes a little bit electron lean, electron deficient, and the other end becomes electron rich. So what started off minding its own business with this symmetric distribution of electrons in the presence of the dipole takes on a dipole moment itself. So this dipole is induced by the presence of the permanent dipole. And now we have some bonding. This negative end here now is in a position to be attracted to the positive end of a permanent dipole. And so on and so on and so on. So this is how the system operates. And we know that the energy of the dipole-induced dipole interaction goes as 1 over the square of the interpolar separation. This is 1 over the square of the interpolar separation, whereas here it's 1 over the cube of the interpolar separation. And furthermore, we can talk about how susceptible elements are to this induction. I can give you two different elements. Suppose I've got argon and next to it I will put helium. They both have inert gas electron configurations, but helium is small and it has a few electrons. Argon is large and it has many electrons. Which of these two, argon or helium, is more susceptible to this electron displacement? You see, it's argon, because argon's larger, it's squishier, it's softer. This is hard. This is like a baseball, this is like a Nerf ball, right? So it can be easily distorted in terms of its charge, and we call this distortion of electrical charge polarization. Polarization is the official term for electrical charge displacement. Electrical charge displacement. And so we can quantify the ease with which electrons are displaced within a chemical entity by a quantity called polarizability. Polarizability. And give it the symbol alpha. And this is a measure of ease of electron displacement. And clearly polarizability is affected by, now watch the fonts here. This is alpha, and then I want to say alpha is proportional to, so I don't know how you differentiate the two. So alpha is proportional to the number of electrons. In other words, the more electrons, the more there are to move. If I only have a couple of electrons and I got a couple of protons, those electrons are more tightly bound. They're less flexible. So the number of electrons and also the size. For equal numbers of electrons, a larger entity will be softer and squishier than a smaller entity. Right? So polarizability scales with electron number and with size. So we reason that helium is going to be low polarizability, whereas argon will be high polarizability. Because when you have a lot of electrons, they have to, by necessity, you know what the filling sequence is. The more electrons you have, those last electrons are farther out. So the positive charge in the nucleus has a weaker hold on them. So therefore, while they're bound, they're a little bit more, they're frisky. You know, they don't sit in their place, move around. All right, so now let's get back to homonuclear species. This is induced dipole, induced dipole. Now that's the third type of interaction. Induced dipole, induced dipole, induced dipole. This is a really fascinating one. It puzzled people for a long time. And it's dominant. It's dominant in nonpolar molecules. Dominant in nonpolar molecules. It's dominant in nonpolar everything. So it's dominant in nonpolar species, atoms and molecules. And here's some examples. Let's go back. Here's argon. Now, if you look on your periodic table, argon has a melting point of 84 Kelvin. And it has a boiling point of 87 Kelvin. Now, I told you whenever you see a solid, you have to conclude that it's held together by some force. So let's imagine we're at liquid nitrogen temperature. We take some argon out of an argon gas cylinder and we flow it through a tube, and that tube is immersed in liquid nitrogen. Liquid nitrogen is 77 Kelvin. Well, that's below 84. So the argon's going to solidify. It's going to deposit on the walls of the tube. And after a while, I'll have argon ice. So I'm sitting there, I'm looking at argon ice. What binds argon to argon? Well, it's not ionic, it's not primary covalent, it's not dipole-dipole. They're all the same. What could possibly bind argon to argon? What's just adhesion because it's sticky? Why? Why? Well, the answer was given to us by a German scientist by the name of Fritz London. Fritz London. And London, he said, I think I can explain this. He looked back over here at dipole-dipole, and he said, you know, we've already come to the conclusion that electrons are in motion. Electrons are not stationary. So he says, imagine if we could zoom in here with a femtosecond camera and take a snapshot. Instead of having a uniform distribution of electrons, suppose that at this instant in time, there's a slight excess of electron density here at around 2 o'clock. And therefore, conservation of charge dictates that there must be a slight electron deficiency at 8 o'clock. Well, if this is the case, what's the consequence for the adjacent argon? Well, this adjacent argon says if this is electron deficient, it's going to pull electrons in this argon and make the bottom right here electron rich, leaving the top left electron deficient, which then causes she told her and he told him, etc., etc. So what is the result here? The result is we have dipoles. Time averaged, it's nonpolar, but it's always dipolar, and this is a tiny, tiny dipole. Tiny. So he called this time fluctuating. The time fluctuating dipole. And it's present in all systems. In all systems. Even a sodium ion has an electron cloud that's in motion. And we don't see this in sodium because the action of this in sodium is dwarfed by the Coulombic force, which is 1,000 times stronger. But this is the only game in town. When you're at 77 Kelvin, there's nothing left. So this is dominant. And the force that comes out of this attractive force, has been termed the London dispersion force. The London dispersion force. And the London dispersion force is a very weak force, and it's, as you would expect, it's proportional to the polarizability, right? Elements that have big electron clouds that are weakly held are going to be more mobile than small atoms that have small electron clouds that are tightly held. So the London dispersion energy goes as the square of polarizability, and as you would expect, it's a very weak force analogous to the repulsive force, right? We're talking about electron-electron repulsion. Where did you see that before? You saw that in the Coulombic derivation, with the Madelung constant. That's the Born exponent. It's a very high number because this is very weak force. So if this is the interspecies separation, this goes as r to the 6th, which makes sense. It's sort of Born-like. So there it is. Now, this has actually got another name. You know, this is not a secondary bond for argon. This is the only bond for argon. So this is a primary bond. So as a primary bond, some people call this a van der Waals bond. A van der Waals bond. So it's a time-fluctuating dipole which leads to a London dispersion force resulting in a van der Waals bond, which for some systems is the primary. And it's not that I can't spell. Van der Waals was a Dutchman, and that's how you spell van der Waals. Okay, so here's the situation. This is the primary bonding in argon. What about, go to your periodic table and look up iodine. Iodine. It exists as the diatomic molecule. It's got a melting point of plus 114 degrees C, and it's got a boiling point of 184 degrees C. So, iodine at room temperature is a deep purple crystal. What holds iodine together? What holds iodine together? Oh, so you're looking at it going, oh, I know, I'm going to go back to that table 4.3, and I'm going to tell you about the iodine. I'm going to write the Lewis structure, and da-da-da-da. That's wrong. That's got nothing to do with it. How does this iodine, bond to another iodine? Well, what's the catalog? Is there a net charge? No. Is there a local dipole? This is a homonuclear molecule that is 100% covalent. What's left? So you have electron clouds here around the two iodines. So iodine is big. It's huge. which means the electrons, first of all, there's lots of electrons, and they've got a giant corral to run around. And so they're running around all over the place, and at any given moment, the right side might be a little bit electron excessive, and the left side might be a little bit electron deficient, net neutral, of course, and then that's what causes the next iodine, and the next iodine, the next iodine. This is the way you describe. How about this one? Methane. We saw methane. How do I form solid methane? When you look at Jupiter, you're seeing solid methane. Do you ever sit there and think, how's that solid methane held together? I bet you never thought about that. Well, I'm inviting you. Think about it. How does this methane bond to this methane? And I can see everybody go, oh, I know. Carbon, hydrogen. It's a polar bond. I got it. It's a polar bond. And you proudly trot out your electronegativities, and you tell me what the percent ionicity is. And I go, no, no, that's wrong. Has nothing to do with it. I'm asking about foreign policy. And you're talking about some state budget, right? I want foreign policy. How do they negotiate with one another? Well, what's the list? Net charge. No, they're neutral. Dipole. No, they're symmetric. What's left? So, solid methane is held together by van der Waals bonds, London dispersion force. Remember that next time you look up at the sky and you see Jupiter, the solid methane. Oh, here's a good example of this in compounds. So here, these are 3 different hydrocarbons. So it's just carbon and hydrogen. Here's propane, octane, icosane. So look at it. It's just CH2, CH2, CH2 with methyl terminals. All right? So they're net neutral. There's no dipole moment. They're symmetric molecules. And you all know what propane is. It's a gas at room temperature used as a fuel, low-grade fuel. Boils at -42. Octane is the principal constituent of gasoline, which we know is a liquid at room temperature. And icosane is a solid. It looks like paraffin. 3 different molecules, all nonpolar. How do I describe the fact that propane's a gas, octane's a liquid, icosane is a solid? Right here. Polarizability. Polarizability, which is proportional to the number of electrons in size. As these molecules get bigger, the electrons have a bigger corral to run around in. It's sort of like a small tank gives rise to small waves, and a big tank gives rise to big waves. And that's what you're seeing. Big waves means bonds. Small waves means the thermal forces present at room temperature disrupt. So that's a good one. I really like that. That's a vivid one. Actually, this is out of your book. This shows this is the whole series. I just chose a few extremes. But look, here's methane, ethane, propane, butane, and on and on and on. And look at, as the molecular weight increases, the boiling point increases. Why? Because the polarizability is increasing. But I don't want anybody telling me that the reason something has a higher boiling point is it has a higher molecular weight. That's not expository. I want to know, it's not mass. It's about polarizability, because mass alone will not get you the time fluctuating dipole. So that's what is showing up here. Really, really, really good. Okay, and now the fourth one, the fourth type of secondary bonding is hydrogen bonding. Hydrogen bonding. And it occurs between, as the name implies, hydrogen and only the most electronegative elements. And that's fluorine, oxygen, and nitrogen, owing to their high average valence electron energy. There's something peculiar here about the combination of high average valence electron energy and the lightest element. And here's what I want you to first be reminded of. I'm showing here the average valence electron energy in order. And we see fluorine has got the highest of the active. I know neon has a higher, but neon doesn't participate in chemical reactions to speak of. So I know there are subtle differences in the electronegativity scales. One of them has fluorine at 3.98. This has it at 4.19. It's a self-consistent set. So what do we see? Here we're up at around 20 electron volts for average valence electron energy, and then it tapers off. something magical happens at around 18 electron volts. What happens? When we put hydrogen in the presence of something that is that strongly electronegative, so let's work with the most powerful example, fluorine. So hydrogen donates its electron to the covalent bond. Fluorine donates one of its 7 valence electrons, and here are the other 6. And we know, because fluorine is strongly electronegative, this bond is very polar, and we can designate the fluorine end as delta negative and the hydrogen end as delta plus. And let's look at this in greater detail. When we start pulling hard on the electron associated with hydrogen, what's left? It's not an atom that has its protons in the nucleus and n-1 electrons. In the case of hydrogen, it only had the 1 electron. And when you pull that electron hard, what you're leaving is something that's essentially a proton. If hydrogen is denuded of its electron, it is a proton. The proton is very special because the proton has a charge of +1, but it's got a volume that's tiny, tiny, tiny. So the charge density is very, very high. So now let's bring up another HF. So here's a second HF. We know that dipole-dipole interactions happen. That was category number 1. So let's start with a simple dipole-dipole interaction. The negative end of the left HF molecule sidles up to the positive end of the right HF molecule. Then the magic happens. You see this non-bonding domain sitting here on the right side? Those non-bonding electrons are dangling way, way out there. And here's this hydrogen over here, and its electron is being pulled so hard by the fluorine on the right. I mean, this hydrogen hardly gets visitation rights to see this electron, okay? So there's these 2 electrons sitting over here, and the hydrogen is looking over there and says, I never get it. I hardly get any time with my electron. But there's these 2 lone pairs, electrons sitting there. And so can you imagine that there's a force that's set up between this lone pair of electrons? Because this fluorine, because it's got so many electrons, it tends to neglect its electrons. It doesn't pay close attention. You know, if you come from a big family, you don't get as much attention as if you're an only child, right? So fluorine, I mean, it's got electrons all around. So if 2 kind of stray off, fluorine doesn't care. So that's what's happening. Here's hydrogen that doesn't have the full impact of its single electron. Here's 2 electrons dangling way, way out. This is a recipe for attraction, and that's exactly what happens. And so a weak force is established between this non-bonding pair and hydrogen when hydrogen is found in a molecule where there's this very, very strong pull on its lone electron. So the hydrogen bond is established in this following manner. And this is a very important bond because it's found in compounds involving hydrogen fluorine, hydrogen oxygen, hydrogen nitrogen. And let me show you what the manifestation of this is. Here's first of all a cartoon from your book that shows this weak force. You see the hydrogen where its electron has been pulled. In this case they're showing water, so this is hydrogen oxygen. So the electron of hydrogen has been pulled towards oxygen. And this distance is about 1 angstrom, and this distance is about 1 3/4 angstroms. So it's greater. I'm not suggesting that this is a double bond off the hydrogen, but it's not something to be ignored. It's very, very strong. And in fact, it's about twice as strong as the next strongest force here. It's about 2 to 4 times the intensity of a dipole-dipole interaction. So it makes a huge difference. Let me demonstrate that with data. So this is a plot I inked in. This is out of your book. It shows the series that I'm going to show, but I kind of like this one because I had a chance to color, and as you know, that's very therapeutic for me, so I need to do this. So first thing I want to do is I want to go across the groups, and I want to show you the impact of hydrogen bonding. So let's start with I used colors of the T. So let's start with the green line here. All right, the green line is group 14. All right, group 14. And what do we find? Here's methane, silane, germane, stannane. Okay, the 4 tetrahydrides, if you will, of carbon, silicon, germanium, and tin. And what do you find? As the size of the molecule increases, its number of electrons increases, its polarizability increases, therefore its induced dipole interaction increases, and therefore, the greater the atomic mass, the greater the boiling point. Everything makes sense. Now, let's go to the next one. The next one I'm going to go over is from, this is group 14. What do I want to do? I want to go to group 15. So that's the blue line. So the blue line is up here. This is stibnene, and this is the antimony compound. This is arsine, which is the trihydride of arsenic, which is used in CVD and precursor making gallium arsenide. They use this over here in building 13. Occasionally you'll hear the sirens wailing and people have to evacuate the building. It's usually a gas leak of this stuff. No, it's good the sirens go off. It could be worse if they didn't. And then we have phosphine. So this is following the same trend. As the size of the molecule shrinks, the polarizability shrinks. Therefore, the van der Waals bond weakens. So by this analogy, and plus these are dipole interactions too, right? These are all trigonal pyramids, right? This sp3 hybridization with a lone pair. So these all have a net dipole moment. And the dipole's getting stronger and stronger according to this formula. And everything's going great. And all of a sudden, ammonia has got this abnormally high boiling point. What's going on? Well, in a case of ammonia, it's not just... here's ammonia. It's not just ammonia with its net dipole moment that's sticking to other ammonias. What's happening in case of ammonia is when another ammonia gets in the vicinity, hydrogen bonds are forming. And those hydrogen bonds swamp everything. And therefore, they give strength to the system that trumps the thermal energy and thereby raises the boiling point of ammonia to values that are higher than arsine and phosphine. Now let's go over to the next. Let's go to group 16. So we start with hydrogen telluride, hydrogen selenide, hydrogen sulfide, fitting the pattern. Smaller molecules, lower polarizability, smaller dipole moments. Everything's fine. And then we get to H2O, and it's up at 100 degrees C, which is higher than even hydrogen telluride. Why? Because the hydrogen bonding is present in water. It's not present in the compounds of hydrogen and any of the other members of this homologous series. If it were not for hydrogen bonding, water would not boil at 100 degrees C. It would not melt at 0 degrees C, and this conversation would take on a very different character. We wouldn't exist. So we need hydrogen bonding. And lastly, let's look at HI. This is the group 17, hydrogen iodide. These are just simple linear molecules. Hydrogen iodide, hydrogen bromide, hydrogen chloride. And there's our prototypical hydrogen chloride. So we're just getting bigger and bigger dipoles, higher and higher boiling points. And finally, we get down to HF, which should be the tiniest. It should have the weakest interaction, and we have a very, very abnormally high boiling point because hydrogen bonding is operative. So you can see hydrogen bonding and the impact that it has on boiling point and properties. And we'll return to this when we talk about conformality in polymers, in nylons in particular, and certainly when we get to biochemistry, because our proteins consist of, among other things, hydrogen and oxygen and nitrogen, and those hydrogen bonds help hold the system together. So at this point, just to summarize, we've seen three types of primary bonding. We've seen ionic bonding, covalent bonding, and in certain instances, van der Waals bonding. And things seem to be working fairly well, but then, you know, there's data. And here's some data that I want you to look at. These are data of electrical conductivity. Electrical conductivity. And up here we have metals, silver at 10 to the 7th Siemens per centimeter, copper at 10 to the 7th Siemens per centimeter. I mentioned last day that graphite has some delocalized electrons. It's 10 to the 4th Siemens per centimeter. And then we get down to the insulators. I said diamond was a good insulator. It's 10 to the minus 11th. There's aluminum oxide, a good ionic compound. And here's PTFE, Teflon, 10 to the minus 16. Well, first thing that you notice is, look at the range. I mean, if you look at the range on the periodic table, look at the range of something like density. So you have lithium's got a density of 0.53, and you got osmium that's around 22. So it's a range of about 40. Huh? Look at this. 10 to the 7th, 10 to the minus 16. A range of 10 to the 23rd. 10 to the 23rd. Secondly, what do we know about the compounds we've seen so far? Ionic compounds, conductors or insulators. We know they're insulators. They've got tightly bound electrons in stable octet configuration, so that's not going to help us. Covalent compounds. Well, the network ones are like diamond. Very, very good insulators. Van der Waals compounds. Let's look at that. How about argon? Do you think argon's going to be a good conductor of electrons? No way. It's got inert gas configuration. Those are the three types of primary bonding, and I can't explain how 3/4 of the periodic table has this abnormally high value of electrical conductivity. Sounds to me like we need to come up with yet another form of bonding. And the answer is metallic bonding. Why is it metallic bonding? Because it's practiced in metals. So let's look at metallic bonding. The need for metallic bonding was brought on by the observation of electrical conductivity. So if we're going to be true to form in 3091, we have to look at the electronic structure. And the first model that attempted to account for the high observed value of electrical conductivity was enunciated in 1900 by a German physicist by the name of Paul Drude. Paul Drude in 1900. What he said was that he could model a metal as a mixture. He modeled the metal as a mixture of positive nuclei plus the inner shell electrons, which he called this whole mix of the positive nuclei and all the inner shell electrons, he called that the atomic core. And then the valence electrons, he said, were separate. So you've got the atomic core plus valence electrons, which he assumed were free. Were free. That is to say, they could move about the material. In other words, they were not associated with any single atom. So we call them delocalized. I think last day I used the term delocalized. And we'll come back to that in a bit. So this is in essence modeling the metal as a solid consisting of cores and the electrons freely moving much in the same way as a gas. So this was termed the free electron gas model. In other words, a gas of free electrons. Free electron gas model. And with this, they had some success. They were able to account for such things as the heat capacity of solids. So the heat capacity of solids they could model. So that was good. And I think there was something else they were able to do. But by and large, this didn't stand up because it wasn't quantitative. So if it's not quantitative, what's that mean right off the bat? No Nobel Prize. You got it. No Nobel Prize for Paul Drude. No quantitative, no Nobel Prize. We'll just put this here. No Nobel. No Nobel. And it's true. If you go through the people that made really important insights, but they weren't quantitative, no Nobel. So it's not quantitative. It's because it can't be tested. Not quantitative. And the second thing is, it was not discriminating. In other words, if you said, assume that something is metallic, then you continue with the atomic core and the gas of free electrons. But that's like saying, all right, silver is a metal and this is how a metal behaves. But what about the earlier question? Why is silver a metal and diamond not acting as a metal? Doesn't diamond have a set of positive nuclei with inner shell electrons? Why do you choose to have the valence electrons of silver moving around, but the valence electrons of diamond not moving around? Well, we know a little bit that he didn't know because we have the benefit of Linus Pauling and the understanding of covalent bonding. But even so, he couldn't help classify insulators and metals, and so that didn't work. That didn't work. So we had to wait almost 30 years for the next installment, and so when we return next day, we'll look at the next installment of the attempt to explain metallic bonding. And what happens in the 30 years between 1900 and 1930? The quantum revolution. So clearly, in 1900, in respect of Professor Drude, absent quantum mechanics, there wasn't much else they could have done. But they're going to stand on the shoulders, the next people, on the shoulders of people who gave us quantum mechanics and explain why we have metals as we do. So let's take a look at a few things before we leave. Oh, the unit of conductivity is the Siemens, named after Charles William Siemens, who was quite an inventor. He was born in Germany but spent most of his life in the UK. He gave us the open hearth furnace, which dominated steel making for a century, laid the first transatlantic telegraph cable in 1875, and something dear to my heart, was an early proponent of electric traction for automobiles. No internal combustion engine. So Siemens is this, and so the unit of Siemens is the reciprocal of the ohm, which when I was your age actually was called the mho. That's ohm spelled backwards. This is electrical engineering. That's supposed to be funny, but obviously the SI Commission decided mho just doesn't cut it. We're going to give it a proper name with a proper recognition. And oddly enough, Ohm, whose unit is the reciprocal of the Siemens, was also a professor in Germany. But when he enunciated his law in 1827, the linearity between resistance and a voltage required to drive a particular current, he was so badly ridiculed at his university that he resigned his position. I mean, people, as I told you in the past, scientific change doesn't come easily. All right, so now, I know Professor Ballinger talked to you a little bit about Midgley. I want to talk to you about one other invention of Midgley's and refer back to all of this shapes of molecules. I call him SP3 Midgley because most of his work that we know today involved SP3 hybridized molecules. And I know Professor Ballinger talked about Freon, which was a refrigerant. Midgley at one point joined the Dayton Engineering Company, which is Delco, which eventually was bought by General Motors. And in 1921, he discovered this anti-knock agent for gasoline called tetraethyl lead. And this is lead. You know, the structure is 6s2 P2. We can hybridize this to give us 6sp3. There's 4 unpaired electrons there. And then we can take the ethyl radical and put 4 of those on. And so this gets diluted in the gasoline, and it goes through the combustion process. And what it does is it actually reduces the potency of gasoline. If the potency of gasoline is too high, when the fuel first goes into the combustion chamber, and then the piston compresses, remember, everything's hot from the previous combustion, the chamber could explode in its own, of its own accord, and if it does so, it will ram the piston up, and then everything's supposed to be moving synchronously. So what you want to do is put something in the gasoline to delay the combustion until the spark plug fires. The sad thing is that there was a superior chemical known already back in 1920. It was ethyl alcohol. And ethyl alcohol, if it had been used, we wouldn't have all the lead in the environment that we have thanks to the use of leaded gasolines for about 50 years. So anyways, this is tetraethyl lead, and this was an invention of Midgley. Now, in the 1970s, along came catalytic converters, which we have to this day. And these are precious metal catalysts, platinum, palladium, and rhodium. But when tetraethyl lead burns, the carbon forms CO2, the hydrogen forms H2O, and the lead forms lead dioxide. And lead dioxide is volatile, and it goes with the exhaust gases, and it will pass over the catalyst. And the catalyst, what's its job? It's to break bonds. And so it breaks the lead-oxygen bond and reduces it to lead. And now the lead alloys with the catalyst. So now you have platinum alloying with lead. Now, what do you think the catalytic activity of lead is? Considering the difference in cost, I'm willing to wager that if lead had any catalytic value, we wouldn't be using platinum. So when the lead alloys with the catalyst, it poisons the catalyst. Hence, in the 70s, the advent of lead-free fuel. So all of these things came together as a result of the need to deal with the absence of the tetraethyl lead necessitated by the onset of catalytic converters. So again, you see where the sp3 hybridization comes into play in a chemical that was used for about 2 generations When it came along, people thought it was fantastic to stabilize internal combustion engines, and the end was dismissed for its toxicity to the environment. The same thing happened with Freon 12, dismissed after 2 generations for its toxicity to the environment. Midgley died about 30 years ago. He doesn't know any of this. Okay, we'll see you Friday.